what I have today, I don't have any slides prepared. Instead, we're going to kind of be working together to put together a Monte Carlo simulation, and I'll explain to you what that is. But the general idea is that we're going to be just kind of using this as a way to review how CUDA programs are put together, what the different steps are, and just to kind of get us thinking, thinking in GPU and thinking in terms of kernels and threads a little bit. So this is going to require a little bit of participation. Not a ton, just someone to say, hey, dude, this is what we do here. I'm going to I'll be driving this thing and I'll be the one actually typing it, but I'm going to be asking you guys, okay, what do I do for this step? And we'll continue on from there. But before we can do anything, I've got to tell you what it is we're actually doing. So that's where the Monte Carlo simulation comes in. Now, Monte Carlo refers to a very broad class of simulation. To be honest, I don't know it terribly well, but the general idea is you're doing some sort of probabilistic sampling, and based on that sampling, you can infer something greater about something else. That something else will change depending on what your application is, but you just use probability essentially to define or estimate something else. So where that leads us, this particular Monte Carlo simulation is to help us estimate pi. The value of pi, 3.14, or whatever else it is. And the way you do that is you take a figure like this, where you've got kind of got this circle inscribed in a square on the coordinate plane. You take a point, just pick any random point in here, and you determine whether it's inside the circle or outside of the circle and inside the square. So what we'll be doing is specifically is we'll be assigning it a 1 or a 0. So if it's inside, it's a 1. And if it's outside, it's going to be a 0. And if it's out here, it doesn't get a value because we're not going to deal with any of these. So our world is fully inside the square. It gets a 1 if it's in the circle and a 0 if it's outside the circle. And you take these values, you take the sum of the interior points, the points inside the circle, divided by the sum of all of the points, or all of those inside the square, and you get a ratio. That ratio is equal to pi over 4. And so you multiply by 4, you get an approximate value of pi. Now, there are much better ways to calculate pi nowadays. This is just an estimate. It's not actually terribly accurate until you use tons and tons of points. But it demonstrates a lot of things on, it demonstrates a lot of GPU usage. It's kind of one of those problems that is what's called embarrassingly parallel, where it's easy to parallelize. And so we want to use this method to kind of show off what we can do with GPU and review the concepts we've been looking at the past few weeks. I got some pseudocode that'll kind of direct us, but to review the steps here again, we want to set up this grid, right? A grid of points. And we want to ask every point, are you inside the circle or not? We need to get the total number of points inside the circle. And then the last step is divide the number of interior points by the number of total points and multiply by 4. That's how we get our answer. So that's kind of our outline. Any questions as far as what we're going to try to do? All right. In that case, I guess we'll get started. So this is where we're going to be working. As you can see, I have basically outlined everything for you. And if something happens to where we need to make a new function or whatever, this is just an outline. This is how I did it when I implemented the example. that I'll be referencing just to see for correctness, but we can deviate and go our own way. This is just, like I said, an outline. So, if you look down here to main, this kind of gives us an outline for our program. We've got this constant side length, which is the length of one side of the square Monte Carlo simulation area. So if we go back here, that side length would be this right here. This would be that same constant, right? And so that's that value, just to help you get a visual on that. So you can see our next step is going to be that we're going to allocate device memory, and we need one array element for every point inside our simulation. So how do we allocate that?
Could you use malloc? Or would you first create pointers, a device pointer, and then give it memory using malloc?
So you're partially right. So, okay. So create a device pointer. But it's not just malloc, it's a different call. Because malloc, remember, would be a host side pointer. So, all right. But we'll get to that in a second. So before we can malloc anything, what do I need to start here?
Pointers. Declare the pointers, the names of the devices, device pointers.
Yes, device pointer. We don't need more than one, actually, because we're just, this is just for device memory, and we only have one set of elements. Okay. So we need a device pointer, so I'll just call it D pointer. All right. Now what? And this isn't just grades. You guys feel free to jump in.
A device pointer. I think you use malloc.
Yes, CUDA malloc. Yes. Okay. I apologize if you said that before. I still can't hear you very well, Grace. I can hear you, but it's just kind of, what's the word? There you go. That's a little bit clearer. All right, CUDA malloc. So what does CUDA malloc take? What's our first parameter here?
The type of the pointer you want, and then the size.
Nope. No, you're thinking of a host pointer, right? So host pointer, you would cast it, you would cast the malloc. So you're thinking not bad, but it's not how we use device pointers. All right, let's give someone else a shot. Let's see here. All right, Evelyn, what do I do to allocate a variable on the GPU? I've got the name declared here, but I need to actually allocate the memory. So what do I do? Oh wow, you are very faint. Any chance you can turn your sensitivity up a little bit?
Not sure.
Oh, there we go. That's a bit better. Oh.
I'm sorry, but let me look somewhere real quick.
Okay. Yeah, if you guys want to pull up a quick reference just to have it, you guys should have access to all of the slides that we've covered in previous weeks, so that'd be a good quick reference to have.
You put the address.
Okay. So address, yep. So
The address where you want the pointer to go. So you use the ampersand and the name of the pointer.
very good. Yes, that's precisely it. Yeah. That is exactly it. Okay. Good. What's the next value we need here? I'll give you a hint. It starts with this.
Integer, size of int.
Uh-huh. Okay. But then how big do we actually need to make it? How many integers do we need?
They be the same as the side length. I'm not sure.
Okay. Well, let's go back here, right? So side length, we said, was the length of one of these sides here. But we want to represent this entire grid inside of this array that we're allocating. So this right here is going to represent D points. So how many integers do we need? It'd be the same as the area of this square, right?
Mhm.
Okay. So what's the area of that square?
It's side times side. I don't know what you have for side length. Side length times side length times 2.
Nope, not times 2. Just side length times side length. You had
Okay.
it. Okay. All right. So that's our malloc call. Gotta have the address, gotta have how much memory we want, and we're done. And just as a good practice, we also want to go ahead and clean up our memory so that we know it's done. So I'm just going to give this one to you. What you call CUDA free device pointer. And notice no ampersand here. We don't need that. It's just the normal variable, just as is. Okay. So we've allocated and deallocated. So our next step in this Monte Carlo simulation is determining what counts as being inside of the circle here. And how do we do that? And I'm not talking programmatically, I'm talking mathematically. And I'll give you this part. So mathematically, the easiest way to do this, or at least the way I've looked at it, if you take a point that's like out here, let me get rid of these for a second. Let's say this is, I don't know, -4 or 6 or whatever. And that's just a point that we have represented. Well, the easiest way to see if something is inside a circle is to see if its vector, right, the length from here to 0, is less than the radius. Because if it's greater than the radius, it has to be outside of the circle. So we just need to know the length of the line from this point, -4, 6, to 0, 0. And the way we do that is called the magnitude of the vector. Now, if you don't, you would be forgiven if you don't recall the math stuff for this. I get that. Like, this is not, we're not mathematicians, so no worries there. But the formula we're going to implement is fairly simple. It's just the square root. So I'm just going to put that square root, and then square root of x squared plus y squared. Right? That's magnitude. And we want to compare that to the radius, like I said. If it's less than or equal to radius, we're good, it's inside. And if it's greater than radius, it's outside. And we use that later on to basically mark each point and see whether it's interior or exterior. So let's do this. All right, there's that. All right. So, if I didn't, I think I said this already, but just to reiterate, this D pointer is going to be our representation of all of our points. Right, that's going to be the grid that we're looking at. Okay, so determine which points are inside the circle. What's going to do that, the kernel we're going to use eventually, once we write it, is the set points up here. It's saying set the point to 1 if it's inside, set the point to 0 if it's outside. That's why it's called set points. So we're going to call this kernel. I'm not going to worry about implementing it just yet. But I want to work through how we're going to call it and how we're going to configure it to be called, right? So that's the kernel name, set points. And we want it to work on a grid basis with sides of length, side length. So how are we going to set up the kernel configuration? And if you don't mind, I'm going to ask you to answer this, Garrett, and tell us how we set up this kernel.
Okay, I am still a little finicky on this. So, I'm trying to think. If we're going, do you want to go off the picture of like the circle and then
Sure, yeah.
where you have this on? Okay, so would you want 4 blocks since there's 4 quadrants?
You could. That's a good thought. But that would actually be a bit different algorithm, to be honest. That's potentially smart. But we're going to look at this as 1 block. All right, so treat it all as 1 block. I should have given you that information to start with, so that's my bad. But knowing that, how are we going to change this? How are we going to set this up?
So if we're doing this 1 block, would you do is it the DIN 2D or the DIN 3D?
Yep.
And do the side length.
Mm-hmm. I'm going to call it block dim here. And I actually learned recently a new way to do this. You don't actually have to use the equal sign. You can just declare a name and put parentheses behind it, and that's it. It's good to go. So there's that. Okay, so that's our block dimension. What about our triple brackets here? What goes in here?
Would it be 1 and then block dim, or 1 comma block dim?
Yep, you got it. All right. And then, of course, you don't know this yet. Well, actually, you do, sort of. So it takes in an array of points and a radius here, right? So how do we translate what we have in main to those values? What do we need inside here? I will refer back real quick. Remember, this is your side length here. Side length is this 1 orange side, which is the diameter of your circle. So remembering that, keeping that in mind, the first thing we have is our points array, which I'll just put that one in this D pointer. It's fairly easy. What is our radius?
You just be side length divided by 2.
That is correct. Yep. Okay. Good. So this next one, we're going to go ahead and sum the number of points inside the circle. And to do this, we're going to use a reduction. We will write that here in a minute. All right, I'll tell you what, I'll hand this one over to Evelyn. It's going to be pretty similar to the kernel we just set up, but this time we're going to set up the reduced kernel. So how do we do that? So we got reduce, right? That's the name.
So we need to sum up.
Yes, but so this is just the kernel watch. We're not worrying about the code for actually doing the summing.
Okay.
All right. So first we got to tell it how many blocks and threads we want. I said before we're just going to keep it to one block, right?
Mm-hmm.
And our threads, what's that going to be? How many threads we want running this thing based on what we've already done?
One,
Now you want more than one thread. So we got one block, right?
one block, and the
Uh-huh.
block dimension.
And then block dim, yeah. Because we want the same number of threads to reduce and come up with the sum of points as we have setting them to begin with. Okay.
Mm-hmm.
All right. And then we've got this array of points or this pointer of points and then a radius here. Oh, I'm sorry. That's a different one. Points and then size. So size here being the number of points that we have.
Okay.
So maybe I'll rename that real quick. All right. So our points is what? What's that variable name that we've got?
Number of points. Is that
The not the number of points, the points array. What value are we using for that in main?
is it the DPTR?
Yeah. Yeah, and that's just PTR just stands for pointer.
Okay.
But yeah, that's it. And then we need the number of points. So what's that going to be?
Number of points.
Mm-hmm.
Is it the in num points? Is number of points, right?
Well, so that's the parameter, but we don't have a value for that down here in main, right?
Okay. So that would be this. Are you referring to side length?
Well, that's close. So we have so let's go back here. Remember, we have a point for every single integer point within this square area.
Uh-huh.
So within this whole grid, we're going to have 1 point for each. You're going to have, like, for example, -8, 8, if that's the size of our square, or, you know, whatever it
Uh-huh.
may be. Each single one of these is going to be a point. So you have to have all of those accounted for. And that's the value we want to put for num points.
So is that supposed to be the like the side length? I don't know how to count the number of points.
Okay. So it's close. So it's going to be the area of this square is the number of points that we need.
So is that the side length times side length?
Yes,
Okay.
that is correct. Okay. And then display on host side. So to break that down a little bit, what I mean here is the reduce is going to put a value inside element 0 of D pointer, which says this is the total number of points on the inside of this circle, right? That's the value we need to get our pi approximation. So we want to transfer that to the host side and then calculate our pi approximation and display it. So let's break that down. So and start with
Name
this.
copy.
Yep, good. Yeah. And this is for anybody now, not just Ethan. Yeah, if you want to fill this in, we'll go ahead and do that. So mem copy, all right. That's good, but we got to have somewhere to transfer to, right?
Okay.
So I'll go ahead and fill this in. We need a host value. I'm just going to call it H. And because C is picky, you have to actually allocate something. I only want a single value here, right? So I can just leave it just like this. I only want one integer, so we'll leave it be. That's it.
Okay.
And now, if you want to help me fill in this mem copy, what do we have first?
Host,
Host, right? Because it's the destination. Okay, good. Next.
device,
Yep. D pointer. Okay. How much are we copying?
the size, number of points, I think. Size of
So
1. Okay.
yeah, just one, because we just want to copy element 0. Now, if we wanted to copy all of the elements, you got the right idea. That would be side link times side link again. But we're just copying one element. Okay, good. And what do we need here? There's value. I've
Put
started
a
it.
mem copy
There's more.
to device to host.
Very good. Oops. All right, good deal. Now I'm just gonna break this up actually. Transfer to. All right. So this part I'm just going to take care of because it's just like any other program. We want to show, we want to print a single value,
Mhm.
and that value is just going to be the output of this function. All right. So I have calc_py. And as far as the inputs to that, what is the number of interior points? What's that value? Or variable name, I should say.
Area,
Nope, we don't have a, well, we do have area, but we don't have that. So interior, remember, is what our GPUs calculate.
Is it H now?
Say it again.
Is it H?
Yes, it is in fact H. So H is returning what our
Wow.
GPU summed up as the total number of points that are inside the circle versus outside. Good.
I see.
And then we need exterior, which is not necessarily exterior. It's actually just total number of points or the area again. So that's going to be side length times side length. Oops, I can't type. There we go. Good. Okay. And then we'll also add in a free here just so that we're making sure to do everything all nice and pretty like. All right. And that's our main. We got through that. Now is the hard part. Okay. So the first thing we're going to use from our main is the set points, right? But we actually need a couple things before then. So we're going to come back to this. So last week we learned about indexing, how to find an index in one dimension. So if you have a 2D thread configuration, you want to find a unique ID for each. We learned how to do that. This is slightly different. Here we actually want the X part and the Y part of the index. So I'm just going to put this out, but just observe, and I'll talk about it here in a second. I'm going to put this as if it is a multi. That's not how you type that. As if it is a multi-block situation. But of course, in our situation, it's only one block, so part of this doesn't apply. But just so you guys see it, here's how you would get the Y part or the row of a thread, should you need it. So block index.y times, nope, block dim.y, that's what it is. So basically all this is doing is saying, give me all of the Y parts, all the y components, and I'm going to add them up. And that gets me to the y level of the individual thread. And then column is going to be the same, but for x. And just to briefly demonstrate here, let's see. Let's say, I don't know. Let's do that. That. Okay. So we can see here, we got all right. So we've got this grid, 2x2 grid. So there's a total of 4 blocks. That's represented by these boundaries. And then each block is 4x4. So that's represented by the individual grid cells here. If we're looking at, let's say this cell, then we're looking at here, I'll put it out to the side, is, let's say we want to look at the x value. So block index.x is 1. Thread index should be 2, right? Because we're here, 0, 1, 2. And so when you add, oops. And so you can add together 1, right, for the block index, times 4 for the block dimension, plus 2 is going to give you 6. And if you go from here in the x direction, you have 0, 1, 2, 3, 4, 5, 6. So it's the 6th thread in just from the x direction. And that's what our column value is, right? So this is column 6 out of 7. And it's the same process with y. So this is block index 1 in the y direction, and actually it's also thread index y in, or yeah, thread index 2 in the y direction as well. So same thing. You end up with 4 to count for these 4 threads, and then 2 more to count for these 2. That gets you to 6. So that's where that those models come from for row and column. And we're going to use these to kind of index it in a matrix-like fashion, which you'll see here in a minute. Man, this has been going by fast. We got 20 minutes left. I may have to take over more than I wanted to, but that's okay. Just get through it. Okay. So let's go back here. We're now in set points. And as I said before, the goal of this kernel is to have each thread set its corresponding element in points to 1 if it's inside of the circle that we're using, and not do anything otherwise. So, and then what we're going to do that is via magnitude. So actually, let's do that first. In the interest of time, I'm going to go ahead and do this for us too. But I will explain it. So here, when I mentioned and kind of explained the whole Monte Carlo method, I mentioned briefly that we're in a Cartesian plane centered at 0, 0. I didn't even necessarily mention it. I just kind of showed it using these coordinates here. that's well and good, and that works for our magnitude calculation well. But the reality is, when we go to schedule a block, I'll just use this for example here. The reality is that scheduling looks like this. I'm just using 16 for reference. That value doesn't really have any special significance, but point is, it's all positive, right? It's all greater than or equal to 0, and there is no origin. It doesn't really resemble the Cartesian plane in any way whatsoever. So if we were to do this magnitude calculation that I talked about over here, we would get a bunch of wrong values because it's not centered at 0. It's centered at, well, 8, 8 in this case. But it's off center, so this doesn't translate to this model. So what we've got to do is translate this to a Cartesian coordinate, and that's what I'm using cart x for. And I will admit I'm cheating a little bit. I figured this out earlier and I've got it pulled up to the side here, but I'll explain it as I go because it's not too big of a deal. So, so column is the x component, right? So it's saying, okay, use your given x component, whatever that is, your x coordinate, and then you just subtract grid length minus 2, or grid length over 2, my bad. So you've put it half a grid back from where it was. And that's how we get negatives and positives, and you center it at x equals 0 rather than x equals grid length over 2, whatever it was. So we just move everything back in the x direction. Y is a little bit harder to explain, but not too bad. There we go. All right. Did I get that right? Pretty sure I did. Yeah. Okay. This one's a little harder. But if we go back here, so in this model, right, y starts at 0 at the top and then just increases as you go down. And of course, that's not how the Cartesian plane works. Y is 0 in the middle and it goes up as you go up and down as you go down. So even if you kind of recenter it, this is the wrong direction. So we flip the direction. That's the -1. And then because it's been flipped, we're off center by half. So we have to add that half back. If it doesn't make sense right now, it's not totally important. This is kind of a niche application. You don't necessarily have to know how to do Cartesian stuff. But if you take, if you look at these two side by side, and then basically just translate point to point what it should be, like this would be, right? This would be -r, r, and then this would be r, -r. And you work through, you can derive an equation for how to flip this into this. And I guess I should start. This is 2r. So you can work through and kind of figure out these equations just based on how the numbers need to line up. Is everybody okay with that enough to move on? I know I haven't done a great job explaining it necessarily. Okay. Okay. And from there, like I said before, we just want the magnitude. And magnitude is pretty simple. Once you have Cartesian coordinates, it's x squared plus y squared, and then you square root that result. So that's all we're going to do. Cart x plus cart y times cart y. And yes, I could use power or some fancy thing to do this, but honestly, I believe it's better hardware-wise, and it's certainly, I prefer just to use multiplication when it's a simple square. If it's past that, I generally use power, but anyway. I think it's actually a hardware performance improvement too, if you don't use POW, but that's just my conjecture. I'm not certain of that. Anyway, this value is the magnitude from any point in our grid, Cartesian grid, the distance from that point to 0. And again, if that distance is greater than our radius, we know that it falls outside of this circle that we're simulating. So let's go back to set points and use magnitude to actually determine this. So somebody tell me what I'm looking for here. I have points, I have radius, I have a magnitude function. How do I put it all together?
Would you just do if magnitude is less than radius, or less than or equal to radius?
Yeah,
And
pretty much. We're missing a parameter to our function though. You get that one for us?
Oh, if would that be radius times 2?
It would be. Yes, you're correct. Okay, good. And you can continue, Garrett, if you want, or someone else can pick it up. What are we going to do if this is true?
Would you set? I'm not entirely sure about how to identify, but you would set the corresponding point in the points array to 1. So
Yeah, that's exactly right. And yes, you're also correct in that we haven't figured out how to do that yet. I mean, oh, haven't figured out is kind of what I mean, not exactly. But yeah, so points something is equal to 1. That's absolutely correct. And that something is actually just our 1D index like we've used before. But we're actually going to do it slightly differently because of what's available to us. So not that. And I know that can be confusing, but just to have a different way to think about it. That value, make sure I've done it right. Yeah. This value is essentially the same as our index. If you go back and look at last class. Now, it's kind of wrapped up in functions, but you can think of it as, since we're in one block here, you can think of it as we have a number of rows. We account for all of the threads in those rows. That's block dim.x. And then we have the number of columns in the row that we're in. So if you stop and think about it, that is accounting for all of the threads in the block that we're in. Now, granted, this doesn't work for a multi-block scenario, but we're not worried about that. And we're just going to use that right here. Good. Okay. That should be all we need. Let me double check here, make sure nothing. Okay, yeah, good. And like you said, Garrett, we use less than equal to. That should be fine. All right, good, good. Now's the fun part. Since we have 10 minutes, I was hoping to kind of work through it, but I'm kind of gonna have to just run through it here. So I'll tell you what we will do. Let's get rid of this. So a reduction is a sum. Well, in this case, a reduction sum is a sum. You can actually reduce all kinds of different operations. But in this case, we'll say it's a sum. Okay, and we'll call that good enough. So let's assume I just have this array here. What a sum is going to do, a reduction, I should say, is it's going to have the number of threads doing the work. So if I have 8 items here, which I do, I'm only going to have 4 threads run. I'm going to have the threads that are, I'm going to have every other thread run to start with, right? So I have a stride of 2. each thread is going to add itself plus the element at stride minus 1. So for this first one, I've got 0 and 1. I've got 1, 0 and 1 again, 1, 1 and 1 is 2, and 1 and 0 is 1. And then we double our stride again. So now the first or 0th, technically, and second threads are going to work. And they're going to add themselves plus stride divided by 2. So that gives us 2 here and 3 here. Right? This would be 0 and it would be 8, right? So you can see we're kind of going 2, 4, and then 8. But there is no 8, so it's just this one. And it adds stride divided by 2, which is this number here. And we end up with 5. That's kind of a crash course in reductions, but that's the quick version. So we're going to write something that does this. I'll kind of try to think through it as we go here too. So the first bit is we have a stride. Stride is always going to start at 2 because we always want to have the number of elements up to start with. If you start stride is equal to 1, then you have every single thread trying to do something else. Basically, the long and short of it is it doesn't work. We're going to allow stride to get up to num points. So what that means is if we would jump outside of the bounds of our array, that means we've covered all of the elements essentially. And then that, this says this is equivalent to, actually, we won't do equivalent to, we'll just use stride times equal to 2. The other thing is called a bit shift. We won't worry about that. Just to get everything taken care of. Okay, and we also need to steal this index again. Okay, so we have this loop. On each iteration, we only want threads to run if their index is divisible by stride. So on the first run, every second thread will go. On the second run, every fourth thread will go. On the third run, every 8th thread will go. On and on and on, depending on how large your array gets. Okay. And then from there, we just have points, index, plus equals, points, index plus stride, stride over 2. And that's it. Eventually, this will put a sum in our element 0 of our array here. I believe so. I'm checking that again to make sure I didn't miss something. I did miss something. This is important something too. Okay, good. So first thing I missed is just a little thread guard here. This is just to make sure we can't go outside the bounds of our array. That's not a huge deal. I mean, it would be if it wasn't there, but anyhow. Okay. Last thing is the sync threads. This is required for this because it synchronizes the block and makes sure every part of the block has done its pass of the thing. Wait a minute. Yeah, I put that in the wrong place. There we go. Every iteration, we want to synchronize the entire block because it's not guaranteed to be in lockstep. So we just want to make sure that everything has been updated from the last pass before we start a new pass. Otherwise, our values get out of alignment. We eventually get the wrong value. Okay. And yeah, this is basically all we want here. So I'm just going to fill in this pi here. we're running out of time, so I'm really just trying to make sure we can get a running program out of this and try to get any questions while I work on that. Okay, so. Okay, so this is just like I said before, 4 times interior divided by exterior. That's how that is. And we should have filled in everything. So, all right, while I'm doing this, any questions on any of the code I've put together? That's not it. I'm trying to type quickly and it's not working for me. So no questions then? Okay. All right then. In that case, we will try to run this thing and see if it actually works. Oh, I didn't put a space there. Oh boy. Okay. That has to be square root f. 39. No points. Okay. 72. Always got to dereference your pointers. So I send a pointer in here instead of the value. So we got to dereference it to get the integer value first. That's what that reference was for. Let's see. Oh, yeah, of course. I did that wrong thing again. Cannot open. Ah, okay. It's because I forgot to put. There we go. Of course. Okay, well, that's no good, of course, but unfortunately, we don't really have time to diagnose it. So, I guess I will. I guess I'll post this into the drive if you guys want to look at it and see where it is. But I've actually got to get to another meeting at once, so I don't have time to stick around and diagnose it, unfortunately.